Okay, sorry about that, guys. And I do want to share my screen so that people watching this can see. There. Okay. So here we go. We've got the periodic table, right? We're going to be talking about nuclear fusion and stuff, right? But we've got element number one here, hydrogen. Hydrogen has one proton. Yes, Orion.
Um, I did just show it, but I have some corrections in there that I would like to have help on.
Okay, well, we're going over that. Okay.
Yeah, sorry.
Okay, that's okay. It's okay. Um, so we've got the periodic table here, right? It's organized by atomic number, and an atomic number is based on the number of protons in the nucleus of an atom, of an element. Okay. So hydrogen has one proton. My mouse clicked me over. Helium has two protons. Lithium has three, and so on. Okay. Each row or period, okay, represents a certain um, level of electrons on the outside. Okay. So, or it essentially represents how many um, orbits or how many layers of electrons there are. So the top there, row one, period one, with hydrogen and helium, has one row of electrons, one orbit. The second period, starting with lithium, ending with neon, has two orbits of electrons. Okay. The third period has three orbits of electrons, and so on. Okay. Vertically, okay, you have the groups. Okay. The mouse. Sorry, hold on. Okay, so vertically you have these groups, okay, and the groups are color coded mostly. Um, but these groups represent elements that have the same number of electrons hanging out on the very outside. Okay, they're called valence electrons. Um, and so these elements have the same sort of behavior as other ones like them. Okay, so lithium, sodium, potassium, rubidium, cesium, francium, those all have very similar behaviors. Okay, because they all have one electron on the very outside orbit. Okay, so, right, we know that atoms have protons that are positively charged and neutrons that are neutral electrically in the center, with electrons orbiting the outside. Electrons are really, really tiny. Protons and neutrons are much larger um, compared to an electron. Okay. And an element, a neutral element or a naturally occurring one, usually has the same number of protons as it does electrons. Okay. That did not change for some reason. Why did that not change? Why is this not working? Okay. So this element that we're looking at here, let me see if I can get this to work again. There we go. Okay. Again, okay. Why didn't it do that? Why didn't it change? Oh, having computer issues, guys. So we have an element, a sample element here. It has seven protons and seven neutrons in the nucleus, and then one, two, three, four, five, six, seven electrons orbiting the outside. Which element would this be? Go ahead and type that in if you can. I don't know what's going on with it. Yeah, nitrogen, exactly. Element number seven. Exactly what you would expect. Okay. What about this guy? Looks like we've got two protons shown in red in the middle there in the nucleus with plus signs, right? Because they have a positive electric charge. Two neutrons in the nucleus and two electrons orbiting the outside. Those are negative, right? Okay. Yeah, helium. Okay. Now, because neutrons and protons are about the same size or in the same mass, and because they're so much larger than electrons, the mass, okay, so how much stuff there is we usually just think about it as the number of protons plus the number of neutrons. Okay, so helium would have a mass of four. Okay, four atomic mass units. Okay. Okay. So, how can you tell what element it is if you look at the structure of an atom? Okay, I need all of you responding to this so I can get an idea of where we're at. And please have your cameras on, please. Okay, so it looks like we're a little confused still, some of us. It's the number of protons is what element number it is, the number of protons. Okay. Okay. So to make atomic nuclei, to make a new atom, you have to have enough protons and neutrons. And those don't just come from nowhere, right? If I want to make a heavier element, say carbon, right, I have to have protons and neutrons. I have to have enough protons and neutrons to put together to make carbon. And so I got to get those from somewhere, right? Well, I get those from smaller atoms, right? Okay. So we start, okay, with hydrogen, okay? Anything heavier than iron, though, is not made in a star. No star anywhere can make an element heavier or more massive than iron. Okay. But everything smaller than that, and everything up to iron, is made inside a star by smashing together smaller elements. So if I want to make oxygen, I smash together two smaller elements, two smaller atoms. If I want to make neon, two smaller atoms. If I want to make argon, argon is element number 18, right? I can smash together two or more smaller atoms, right? So argon is element 18. I could smash together neon and oxygen, and I could get argon, right? So that's we got to smash these things together. But we need enough power, enough energy, enough pressure to do that. Okay. So let's look at the life cycle of a star. Oh, actually, I'm sorry. Before we go into the life cycle of no, 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 we'll do this. We'll do this. Okay. Um, a star starts as stuff, just free matter floating in space until that matter gets close enough that the gravity of that matter starts pulling the pieces together. Okay. And eventually enough stuff gets pulled together that it starts to form a star. Okay. But it doesn't become an official star until it starts fusing atoms. Okay. It's got to start fusing atoms. That's when it really becomes a star. The smallest stars, main sequence stars, we call them, hold on, Damien, are fusing together hydrogen. They're smashing hydrogen together in their core to make helium. It actually takes four hydrogen atoms to make one helium because helium has two protons and two neutrons in the nucleus. Hydrogen has no neutrons. It just has one proton. So you need four hydrogens, smash them together to get helium. Okay. So that picture there is wrong. I need to fix that. Okay. Um, yeah, that's not that. I'm so sorry. I don't know who put that one together, but it's wrong. I should have fixed that. So let's, Damien, what's your question?
Yeah, so the picture back when it said whatever it said, I don't remember the title. Anyway, it said that at the bottom that it said, it starts from supernova, then a normal,
No, it does not start from a supernova. It starts from
I
a
mean,
nebula.
yeah, a nebula, then massive star, red giant supernova, and it either leads to a black hole or neutron star.
Yeah, we'll
I
we'll
don't
get to
know.
that later. We'll get to
How
that
does that
part of it later.
work?
We'll get there, I promise. Okay. We want to start with step one though, right? Okay. So step one, we've got hydrogen atoms fusing together to make helium atoms. Okay. So if we're going here, what is fused? Okay. This is actually, oh, I gotta fix all of this. I'm so sorry. What is fused? Hydrogen atoms. Hydrogen atoms, right? Number of protons fused. Um, we'll say two, kind of. What element has produced helium? Number of protons in resulting atom, two. Okay. Well, it doesn't end there, okay? But it takes more energy to fuse together larger atoms. So I fuse together, I smash together hydrogen atoms, I get some helium out of it. Then what? Well, then I run out of hydrogen, and the gravity of the star starts pulling everything in again. Okay. So it's pulling everything in until the pressure and the energy and the heat and the pressure and the energy inside the core gets so big that it starts to smash together the bigger atoms, the helium atoms. Okay. Okay, so let's do this. Let's look at this. Go here. Okay. When we start smashing together helium atoms, we get bigger elements. Okay. If we smash together three helium atoms, we'll get carbon. Okay. Right, so let's put that in here, right? Now, when that happens, I'm going to put three helium atoms at the beginning, right? Huh, three helium atoms. And I'll just put two hydrogen atoms here. It'll be fine. Okay. Number of protons fused. Well, each helium atom has two protons, so that's six, right? Which means we're producing carbon. Number of protons in resulting atom, six. Okay. Right. Now we have like intermediate steps here. It is just like those mobile merging games. You are absolutely right. Just like them, like 2048. Okay. We have some intermediate steps, right? That is fine, Adeline. But ultimately, we're going to look at each step because each of these steps is when we transition types of stars. Okay. So when we're fusing helium atoms to make carbon atoms, we usually have a much larger star because when helium atoms are fused together, they release more energy than when hydrogen atoms are fused together. Hmm. That's a great question, Nick. So Nick said, if we smash together six hydrogen atoms, are we going to get carbon? Yeah, no, no, we're not. And the reason is that they are going to smash together and form a helium atom long before you can get six of them together. Okay. So theoretically, could you do that? Sure, but that doesn't ever actually happen, right? You get a bunch, if I had millions of hydrogen atoms to get next to each other and put in enough energy and enough pressure that they started to fuse together, they would form helium atoms first. And then those helium atoms would smash together, would fuse to form carbon atoms. Okay. So that is a great question there. Well, let's say we've got carbon atoms, right? Carbon atoms. Hmm. Well, how many carbon atoms do you guys think are going to smash together? Let's look and see. Let's see if our presentation helps us out. If I smash together a carbon atom, ooh, with a helium atom, why is this not doing it? Oh my gosh. I get oxygen. Ooh, that's kind of nice. And then if I smash together, what's going to make a silicon? Silicon's element 14. Hmm. See, oxygen's element 8. If I smash together two oxygens, I'm not going to get element 16 or element 14. I'll get element 16. So what is going to smash together? What's going to fuse to form silicon? Hen has it. Seahorse, you've got it. Armadillo's got it. So oxygen doesn't have helium in it, but you need the helium to create the oxygen to make it. Once those elements are fused together, once you fuse a helium with a carbon, it's no longer like either helium or carbon. It's oxygen. It becomes a new thing. Okay. So yeah, so let's put this in here. You know what? I'm gonna say a carbon, one carbon and one oxygen atom. Well, that's 14 protons, and we get silicon, right? Hmm. Well, what would happen next? What did we say was the biggest element that stars could fuse? Iron, right? Ooh, iron. Okay. Well, how many protons does iron have, guys? What element number is iron? Hmm. Yeah, it's element 26. Okay. So this keeps going, right? As you can see here, okay, as stars get bigger, okay, they fuse together smaller atoms towards their outside. Okay, so a star like our sun is fusing hydrogen and making helium in the core. But when it runs out of hydrogen, okay, it's going to expand into a red giant star, and then it will be fusing bigger elements in its core. And eventually, and it'll keep doing that until it runs out. But as it does that, some of those elements are going to kind of push outwards a little bit. So it's going to have smaller elements in layers like you see there. And so you're going to see these succession of um, smaller and smaller elements being fused together as you move towards the outside of a star. Okay. Okay. So great question, Nick. Great question. So we've got, if we go here, if we want to create iron, iron is element number 26, which means we have to have 26 protons to start off, right? What are we going to get? Well, if we take a silicon atom, right? Silicon is element 14, right? So 26 minus 14 is 12. Hmm. What's element number 12, guys? Let's look. Let's see if I can bring up the periodic table here. Periodic table of elements. Okay. Ah, no, no, go away. Go away. Okay. Open in full screen. Here we go. Number 12, magnesium. Ooh, magnesium. Okay. All right, that's element 12. Carbon is element 6. So I'm going to guess that we probably one silicon atom and two carbon atoms. That's my guess. It makes sense, right? We get that's 6, 6, and 14. It's 26, right? Um, it could be one silicon and one magnesium. It could be three carbons and an oxygen. Just kind of depends on what's there in that center, but probably a couple carbons and a silicon or a silicon and a magnesium. Okay. What's really important is that we understand that as we fuse together the smaller atoms, okay, we get bigger and bigger atoms, and those fuse together until we run into iron. And the number of protons we smash together should be the same as the number of protons we end with. Okay, so if we run out, if stars stop fusing elements when they get to iron, how do we get all this other stuff? How do we get gold, guys? And silver and mercury? Like rhodium is how we make white gold, right? We take regular gold and we take rhodium and chromium and silver and mix it together and put it on top. That's how we get white gold. Okay. Um, we've got indium and gallium here. Indium and gallium are used to make screens on your phone. We've got tin. We use that to make cans for food. All this stuff exists. There's a lot of it out there. So how do we get it? Where does it come from? Well, it turns out kind of the same way. We just need more energy and pressure to do this. Okay. So, other types of nucleosynthesis. So, nucleo means nucleus, right? Synthesis means to create. Okay. Yes, Adeline, different combinations of the same atoms. Okay. Um, we've got three different kinds of nucleosynthesis that are not what happens in the center of a star. We've got Big Bang nucleosynthesis. That's the creation of all the hydrogen and helium atoms when the Big Bang occurred, right? At the very beginning of the universe. Okay. That's where all the hydrogen and helium came from. Okay. So that's important, right? But anything heavier than iron is created when stars explode. So what happens is when a big, massive star runs out of fuel, when it can't fuse the stuff together anymore, when all that's left in its core is iron, the gravity pulls it back in, right? There's nothing pushing, no explosions pushing it out. So the gravity pulls it in until it smashes together something really, 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 really big. Multiple irons, for example. And that produces so much energy that it blows the whole thing apart. We get what's called a supernova. Okay. Well, that's how we get the bigger elements. That gravity from a dying star smashes together those irons with other things that are in there and it blows the star apart. And so we get bigger elements, all of the bigger elements. That's where they come from. Okay. We also have cosmic ray spallation. Okay. Cosmic ray spallation is a little bit different. Okay. And really, what cosmic ray spallation is we take some bigger elements that were made by fusion and the cosmic rays or energy, light, X-rays from supernovas, from dying stars, go out and break up those atoms a little bit, create slightly smaller ones. Okay. So let's write those down on our show it. We've got the Big Bang nucleosynthesis, right? We've got supernova nucleosynthesis, and we've got cosmic ray spallation. I'll let you get those descriptions from your stuff, right? That is interesting, Adeline, and but it turns out that carbon and helium do not actually kill us when we breathe them in. What kills us is the lack of oxygen. There's nothing poisonous about helium. It's just that it's in the way. Okay. Now let's link this, right? Apparently I can't speak today, guys. Let's link this to our life cycle of stars, show it, right? So how do stars start off, guys? Oh, actually here. Let's do these questions really quick. These sample checkpoint questions first. What of lighter elements smash together or fuse to form nuclei of heavier elements? Definitely not, Muhammad. Definitely not. Um, it is A, protons and neutrons. So a question like this, you got to read carefully, right? B has electrons and proteins, not proteins. C says photons and neutrons. Photons are little packets of light. D says protons and nephrons. No, nephrons are in your kidney. So just read carefully, right? Okay. Question two. Which type of nucleosynthesis produces massive amounts of hydrogen and what just happened? And helium. Okay. Lots and lots and lots of hydrogen and helium, just those two smallest atoms, elements rather. Yeah, so let's put our answers in the pair deck, right? Yeah, Big Bang nucleosynthesis. Okay. Then, and this is not going. I don't know why this is not showing. So when a star begins to produce what, it'll collapse under its own gravity to become a neutron star or a black hole. At what point will it no longer work as a star? Yeah, iron. When it starts making iron. Good. Okay. Ah, why? Okay, so let's talk about X-ray emissions. What is going on? What? Okay, sorry. I don't know what's going on. It's not. Okay. Okay. We're gonna skip that pulse check really quick. Recap again, heavier elements. Looks like most of you are getting that. Okay, X-ray emissions. Okay, so let's talk about black holes. A black hole is a place that is so dense, there's so much matter, so much stuff that, that it creates an incredibly high gravity, a gravity so high that nothing can get out. Okay. Well, when that happens, sometimes X-rays are spit out from the edge, okay, before they get all the way into the black hole. Okay. And that kind of gives us some clues about what's going on. Black holes can be really, really, really tiny volumetrically, right? They don't take up a lot of space, especially compared to how much stuff there is. You can have black holes that have more matter than our entire solar system, but they're smaller than the Earth. Imagine that. Imagine all of our planets and our sun smashed into a spot the size of our moon. That's insane. It's crazy. Absolutely nuts. Okay. Oh, yeah. See, why is it doing this? Okay. So, how do we figure out they're there? Well, we look at the gravitational pull. We see the stuff that is spit out. Okay. As stuff swirls in towards the center of a black hole, lots of things are happening on the outside. Okay. What we call the accretion disk, and those spit out light. Okay. Um, so what's the relationship between the amount of X-rays emitted and the size of the black hole? Yeah. The more X-rays, the bigger the black hole. That means it's pulling more stuff in faster, which means on the outside, as stuff is getting pulled closer, X-rays are getting spit out everywhere. Okay. And we also see the gravitational effect, right? The Milky Way, the Andromeda, all the galaxies we know of that we can see seem to be orbiting a black hole, right? The black hole, the gravitational pull of the black hole is what's holding it all together. Okay. So, things we use, X-ray telescopes, gamma ray telescopes. Again, X-rays and gamma rays are both types of light. Okay. We look at gravitational pull. How are things out in space moving? Right? If they're moving in a way that seems kind of weird, we got to figure out why. Right? If they seem like they're getting pulled in a direction, but we don't know why, we look towards that direction. We say, hey, there's got to be something pulling it. We also now have LIDAR, okay, that detects gravitational waves. It's fairly new, just within the last few years. It's really, really cool. Okay. So, which of the following is not used by scientists to observe X-rays and gamma rays? Yes, any black hole would have sufficient gravitational pull to yank you in. So it turns out telescopes on Mount Everest. We don't really have telescopes on Mount Everest, guys. Okay. Okay. Next question. Ah, what information do black hole detectors not provide? What can we not figure out here? Yeah, the power of a black hole. Okay, and our last question about X-rays. How do scientists know that black holes exist when they don't emit light? Yeah, they're not matching up. It's having problems for me too. I'm trying to get these things to match up and it's not. Yes, X-ray emissions, the gravity, gamma ray emissions. Good. Good. Looks like you guys have it. Okay, let's talk about the life cycle of stars. Okay. So we're gonna skip ahead here. Okay. Kind of address that question. Just a second, Orion. Address that question that Damien had. But Orion, you had a question about the nucleosynthesis stuff. What's up?
I would like to, with you, do stay on and you help me with the checkpoint, please.
That's fine.
Also, how if that is true in the stars like energy, how do we know that black holes are near us when we if they can suck in how can we stop the gravitational pull of a black hole?
We can't. So we
Okay.
cannot stop the gravitational pull of a black hole. You can't stop gravitational pull. It's there.
Okay, so thank
Okay.
you. So after this we'll do it together.
Yeah, we can work on stuff. Okay. I'll stay on a little bit. Life cycle of a star, it's um, pretty plain. We've just got it's vocabulary, really, guys. But ultimately, what's happening is mass is grouping up, pulling stuff together until it starts smashing together or fusing atoms. When it runs out of some lighter elements, right? Sorry. So matter starts pulling together, right? That's gravity. Okay. Anytime there's matter, anytime there's stuff, you have gravity. Okay. And it pulls in until there's enough pressure and energy to smash together or fuse elements. Okay. It's going to smash together the smallest ones first. Fusion creates outward pressure, right? It's a big explosion. Okay? It's a really big explosion. So when you have enough pressure that you're fusing together lots of stuff, it pushes back out. And then you have a star that's fusing light elements for a while, and that's called a main sequence star, fusing together hydrogen and helium. Okay? Eventually, it runs out, and there's no outward pressure anymore. So it shrinks in until it starts fusing together heavier elements, and then you get more big explosions, right, that push out. The bigger the explosion, the more it pushes out. Right. So our star, for example, is going to go from its size when it runs out of hydrogen, it's going to start fusing together bigger elements like helium and carbon, and it will expand into the size of a red giant because of those bigger explosions, right? It's not going to have more stuff, but the explosions are going to be bigger, so it's going to take up more physical space.
So theoretically, if I'm correct, then
Mhm.
after it reaches to red giant, it should become a planetary nebula eventually into a white dwarf.
Yes. Yeah. So our
Or if
star,
it doesn't follow how the chart says, it could go from red giant to red supergiant and
no,
lead the other direction.
that can't
If
happen.
that happens.
That cannot happen. And it all has to do with how much matter, how much stuff there is to begin with. Okay. So how big a star is and what happens to it, which path it follows, all comes down to how much matter there is when it starts. Okay. Um, you're never going to have a red giant explode into a supernova. It can't happen. Okay. Because there's not enough stuff to create a gravitational pull strong enough that it smashes together heavy enough elements to create a big enough explosion. Okay. So our star, right, it's going to become a red giant and then it's going to run out of carbon and it's going to pull back in, right, until you get what's called a nova. You get a small explosion. Okay. And what's left is a white dwarf with what's called a planetary nebula, which is kind of the leftovers that got spit out when you got that smaller explosion. Okay. And a white dwarf is very, very, very small. Okay. And it's dim, relatively speaking, and it's fusing together carbon. Okay. If there's a lot more stuff there, if you have a massive star, something much bigger than ours, it's going to go from a main sequence where it's fusing together hydrogen into a red supergiant. It'll get really, really, really big. Okay. And it really comes down to the fact that it has so much stuff that it's fusing more stuff together at one time. So instead of 100,000 helium atoms getting smashed together every second, it'll be 100 million helium atoms getting smashed together every second. So more outward pressure, more explosions. Okay. So no, there's nothing else it could be before it's a nebula. So a nebula is just a collection of matter. It's just stuff out there, gas and dust out there that kind of close together out in space. Other questions about the life cycle of a star? Okay, so you're going to just fill in all of this. Okay, you're going to fill this in with the vocabulary terms, right? So this is going to be a nebula, right? All stars start as a nebula, right? Then they all become ooh, a protostar, which a protostar is just it's an in-between stage. All the stuff has started to gather together from the nebula, but it hasn't started fusion yet. Okay. Right. And then it becomes a main sequence star where it's fusing hydrogen. And then after that, a low mass star is going to become a red giant, right? Main sequence, a high mass star is going to become a red, or it's going to become a supergiant, right? Usually a red supergiant. Okay. A red giant, when it explodes, is going to become a planetary nebula with a white dwarf in the middle, right? A supergiant is going to go supernova. It's going to have a really big explosion. And after that, if it's really, really big, it's gonna become a black hole. And if it's not really big, if it's not quite big enough to make a black hole, it's going to become a neutron star, which is it's kind of like a white dwarf, but not really. It's a lot brighter and stuff. So nebulas can be massive. The Eagle Nebula, for example, let me show you the Eagle Nebula. And this is the Eagle Nebula. It's called they call it like the Fingers of God or something like that. But it is hundreds of light years across. Okay. Tons and tons and tons of gas and dust out there in space. Okay. And it's dense enough that it's pillars of creation. That's what it is. Thank you. The pillars of creation. Okay. Um, it's dense enough that it's blocking light, which is why we can see it. And this that matter is getting pulled together, and there are stars being created in there all the time. All the time. Um, the matter's not gonna go on forever though. Like it'll eventually get all used up or not come together and create a star. So, okay. That's about all we've got today. We're going to skip these questions really quick. Here is our exit ticket for today. The password is nucleosynthesis, but it's super, super important that you watch that video before next week. Okay, there's an experiment for you to do. Okay, before our class next week. I'm going to focus next week on writing up the data, like how we analyze data and how we write it up so that other people can look at it, so that other people can compare their results, so we can have good scientific collaboration. Okay, so watch that video, do the experiment if you have the supplies, and we'll write it up together. Okay. Have a wonderful week, everybody. Stick around if you have more questions.